Hello and welcome back. So in the previous course we covered one of the most useful and fundamental law, which is nothing else but Ohm's law. Ohm's law is a law that states that the voltage across a resistor is directly proportional to the current flowing through the resistance. In other words, the greater the current passing through a resistor, the greater the voltage drop across it. We also know that when current is flowing through a resistor, some amount of heat is dissipated at resistor. That means, in a particular amount of time, certain power is consumed at resistor. So again, whenever large current flows, large amount of heat gets produced, and that will burn the resistor. And to avoid this, use high power components that can handle the large amount of current flowing through it. We have seen that the instantaneous power can be calculated with one of these formulas, but we have also seen how to calculate the total resistance when the resistors are placed in series or in parallel. So in this course we will start by solving the total resistance of a resistor network. After we finish that, we will see how to calculate the value of a resistor when it's used to limit the current through an LED. We will learn about voltage dividers, where we will find out how to get basically a lower voltage from a higher one. And last but not least, we will see another usefulness of resistors other than limiting the current through a circuit. So buckle up and let's get started! As a special introduction to calculating total resistances, electronics teachers just love to subject their students to finding that of crazy convoluted resistor networks. A tame resistor network question might be something like, what's the resistance from terminals A to B in the circuit? So the question is, what is the total resistance seen from terminal A to terminal B? In order to solve such a problem, start at the back end of the circuit and simplify towards the two terminals. So in this case, R7, R8 and R9 are all in series and can be added together, right? These three resistors are in parallel with R6, right? So these four resistors could be turned into one with a resistance of R6 in parallel with R7 plus R8 plus R9. Now we can see that R4 is in series with this resistance that we just calculated and in series with this R5. So we can add them together and the final resistance will be in parallel with this R3. So our final circuit will look something like this, and since these three resistances now are in series, the total resistance between the terminal A and B will be the sum of these three resistances. And voila, this is how you calculate the total resistance of this resistor network. Alright, let's move further to our current limiting resistors. So resistors are key in making sure LEDs don't blow up when power is applied. By connecting a resistor in series with an LED, current flowing through the two components can be limited to a safe value. Now the question is how to find out the value of the resistor that we should use in order to not blow up this LED, but also to provide enough current for the LED to glow. That's a good question. And the answer is that we have to dig deeper into how an LED works. So when sizing out a current limiting resistor, look for two characteristics value of the LED, the typical forward voltage and the maximum forward current. As an example, here is a datasheet of a common white LED. So this is how it looks like. It has two terminals and the longer leg is the positive leg and the shorter one is the negative leg. By knowing which leg is the positive and negative, it helps us to place the LED in the circuit in a correct way. We will see how to do that in a moment. So what we are interested in right now is the typical forward current and forward voltage drop. Let's scroll down a little bit and there should be a table with absolute maximum ratings. Alright, here it is. And the first parameter is exactly what we were looking for, continuous forward current. So the continuous forward current is the recommended current that should pass through our LED in order to glow fully and also to not burn it out. This particular LED requires 30 milliamps but this can differ slightly from LED to LED. The other very important parameter that we should find is the forward voltage. Alright, here it is. So the forward voltage is the voltage that the LED will drop across it. So this particular LED has a forward voltage drop between 3 and 3.6 volts. Let's say it's 3 volts. And this means that if we were to power our LED from a 9 volt battery, the voltage after the LED will be only 6, because 3 volts is dropped across the LED. This also means that the voltage of the power source cannot be smaller than this forward voltage drop, because otherwise the LED will not work. Just as an example for better understanding, I created this fancy circuit where we have an LED, a resistor, and a power source of 9 volts. By connecting a voltmeter across the LED, we can find out the forward voltage drop, which is approximately 1.9 volts. The voltage before the LED is 9 volts, since our battery is 9 volts as well, and the voltage after the LED is one forward voltage drop less. So 9 volts minus 1.9 volts is 7.1 volt. Alright, so again, the typical forward voltage is the voltage which is required to make an LED light up, and it varies usually somewhere between 1.7 volts and 3.4 volts, depending upon the color of the LED. The maximum forward current is usually around 20 milliamps for basic LEDs, and the continuous current through the LED should always be equal to or less than that current rating. Once you've gotten a hold of these two values, you can size up a current limiting resistor with the following equation, where Vs is the source voltage, usually a battery or power supply voltage, Vf is the forward voltage, and If is the forward current. So for example, assume you have a 9 volts battery to power an LED. If your LED is red, it might have a forward voltage around 1.8 volts. Now, if you want to limit the current through this LED to, let's say, 10 milliamps, use a series resistor of about 720 ohms. Alright, so I hope you understand how to calculate the value of the resistor. If you have any doubts, feel free to leave a comment below. The next very important circuit that we are going to talk about is called as voltage divider. A voltage divider is a resistor circuit which turns a large voltage into a smaller one. Using just two resistors in series, an output voltage can be created that's a fraction of the input voltage. Two resistors, R1 and R2, are connected in series and the voltage source is connected across them. The voltage from Vout to ground can be calculated using the following equation. So for example, if R1 is 1.7 kΩ and R2 is 3.3 kΩ, a 5 volt input voltage can be turned into 3.3 volt at the output terminal. Alright, so voltage dividers are very handy for reading resistive sensors like photocells, flex sensors, force sensitive resistors, etc. As you can see here, one half of the voltage divider is a static resistor and the other half is the sensor itself. The output voltage between the two components is connected to an analog to digital converter on a microcontroller to read the sensor's value. Almost every environmental measurable parameter is in analog form like temperature, sound, pressure, light, etc. And an analog to digital converter, or in other words ADC, is a circuit used to convert the analog signals such as voltages to digital or binary form consisting of ones and zeros. The last thing that we are going to talk about is pull-up resistors. So a pull-up resistor is used when you need to bias a microcontroller's input pin to a known state. One end of the resistor is connected to the MCU's pin and the other end is connected to a high voltage, usually 5 or 3.3 volts. Without a pull-up resistor, inputs of the MCU could be left floating, and there is no guarantee that a floating pin is either high or low. Pull-up resistors are often used when interfacing with a button or switch input. The pull-up resistor can bias the input pin when the switch is open, and it will protect the circuit from a short when the switch is closed. So in this circuit, when the switch is open, the MCU's input pin is connected through the resistor to 5 volts. When the switch is closed, the input pin is connected directly to ground. The value of the pull-up resistor doesn't usually need to be anything specific, but it should be high enough that not too much power is lost if 5 volts or so is applied across it. Usually values around 10 kΩ work well.